In 1846, an unusual prediction reached the Berlin Observatory after months of mathematical detective work. The French mathematician Urbain Le Verrier had calculated that an unseen world should be disturbing the orbit of Uranus. On September 23rd, astronomer Johann Gottfried Galle pointed a telescope toward the predicted region of sky. There, less than 1 degree from Le Verrier's calculated position, he found the planet now called Neptune. It was an extraordinary demonstration of a quiet idea. Something invisible could reveal itself through gravity. Yet the path toward that realization had begun thousands of years earlier, long before telescopes, equations, or anything resembling a black hole. You can imagine yourself standing beneath one of those earlier skies, where darkness feels deeper than it does today. There are no electric lamps glowing beyond the horizon, no aircraft cross the constellations, no satellites wander silently between the stars. You hear insects moving through dry grass. A fire crackles somewhere behind you, carrying the faint smell of smoke into cool night air beneath your feet. The ground still holds a little warmth from the vanished sun. Above you, the universe appears almost impossibly crowded. The Milky Way stretches overhead like pale smoke. Bright planets drift slowly against fixed constellations, while the moon changes shape with reassuring regularity. To you, these lights are not distant nuclear furnaces scattered across a galaxy. They are patterns, clocks, signs, and companions. For early human communities, the sky provides information essential to survival. The changing position of stars can announce seasons. Lunar cycles offer convenient measures of passing time. The sun determines the rhythm of work, migration, planting, and harvest, long before anyone asks what gravity can hide. Humanity first learns what the heavens can reveal. Some of the earliest surviving systematic astronomical records come from Mesopotamia. Babylonian observers carefully tracked planets, eclipses, and unusual celestial events across generations. You can picture a watcher climbing to a rooftop after sunset. Warm stone presses beneath his sandals, while the evening air carries dust and cooking smoke through the city. He has no telescope. His instrument is patience. Babylonian scholars gradually recognized repeating celestial patterns and developed sophisticated methods for predicting events such as eclipses. Their astronomy mixed practical measurement with religious interpretation, because separating those worlds would have seemed strangely artificial. An eclipse could be mathematically predictable and politically ominous at the same time. One curious Babylonian practice involved substitute kings during periods considered astrologically dangerous. A temporary ruler might symbolically absorb threatening celestial consequences, while the actual king remained protected. The universe, apparently, already required administrative paperwork. Farther west, Egyptian communities connected celestial observation with agriculture and calendars. The annual appearance of Sirius before sunrise became associated with the seasonal cycles surrounding the Nile. You feel how natural these connections would have seemed. The heavens change, the river changes, crops grow, generations pass, and the patterns appear woven together. Nothing in this familiar sky suggests an object from which light itself cannot escape. Even darkness seems ordinary. Dark regions between stars are simply places without visible lights. The possibility that darkness might represent an object rather than an absence requires concepts humanity does not yet possess. Those concepts begin slowly forming around the Mediterranean. Ancient Greek thinkers increasingly searched for physical and geometrical explanations of celestial motion. Their proposals differed dramatically, and surviving evidence leaves historians debating how widely some unconventional models were accepted beyond small scholarly circles. Aristotle offered one of the most influential cosmic pictures. Earth rested near the center, while celestial bodies occupied a realm fundamentally different from the changing world below. Heavenly motion appeared regular, circular, and enduring. This was not foolish reasoning. If you stand outside without modern instruments, Earth does not feel as though it rotates rapidly. You feel no enormous orbital motion beneath your feet. Instead, the entire sky seems to turn around you each day. The evidence of ordinary experience favors stillness. Other thinkers imagined something different. Aristarchus of Samos proposed that Earth moved around the Sun centuries before Copernicus would develop a far more influential heliocentric system. His proposal did not conquer ancient astronomy. Among the difficulties was the apparent absence of stellar parallax. The tiny positional shift nearby stars should display as Earth changes location. Ancient observers could not detect it because the stars were vastly farther away than their instruments could establish. Sometimes missing evidence is simply too small to see. Meanwhile, astronomers became increasingly skilled at measuring what they could see. Hipparchus compiled influential observations of stellar positions and brightness during the 2nd century B.C. He is also associated with recognizing the slow shifting of Earth's rotational orientation through the phenomenon called precession. You might imagine the patience required. Night after night, the same stars return, yet across generations and careful measurements, the supposedly unchanging heavens reveal tiny differences. This habit becomes crucial to everything that follows. Observe carefully, record patiently, compare later. Around the 2nd century A.D., Claudius Ptolemy assembled a sophisticated mathematical framework describing planetary motions around a stationary Earth. His system used combinations of circular motions to reproduce the complicated paths visible in the sky. Mars presented a particularly interesting problem. Normally, it moves gradually against the background stars. Then, during part of its cycle, it appears to slow, reverse direction, and later continue forward. You can watch this without understanding why. Ptolemaic astronomy provided mathematical machinery capable of representing such behavior with impressive usefulness. It survived not because generations of scholars lacked imagination, but because it worked reasonably well for the observations available. Still, something important remained absent. Gravity had not yet become a universal physical principle. Light was not understood as something with a measurable finite speed. Stars were not recognized through modern physics as enormous distant suns. Without those ideas, a black hole could scarcely become a meaningful question, and yet nature was already making them. Long before the first human looked upward, massive stars had formed, burned through their fuel, and died. Some almost certainly collapsed into objects whose gravity trapped light behind horizons. The universe did not wait for humanity's mathematics. As you stand beneath that ancient sky, perhaps one of those invisible objects is already somewhere overhead. You cannot see it. You cannot hear it. You cannot know that it exists. But its gravity is there. Thousands of years will pass before another generation of observers begins changing the cosmic picture again. Old manuscripts will travel between cultures. New observatories will sharpen measurements. Eventually, Earth itself will lose its privileged stillness. For now, however, you remain beneath the naked eye heavens. The air grows colder against your skin. The fire behind you settles into glowing embers, and the Milky Way continues its silent passage overhead. Humanity has learned to measure the sky. Understanding its darkness will take much longer. The stars above you remain much the same, but the questions beneath them have begun to change. After generations of watching seasonal risings, wandering planets, and eclipses, ancient scholars increasingly ask something more difficult. They want to know not merely when the heavens move, but why their motions take the forms they do. You find yourself entering a Mediterranean world where astronomy slowly becomes entangled with geometry, philosophy, and argument. The night air smells of olive wood smoke and salt carried inland from distant harbors. Stone walls release the day's stored warmth beneath your fingertips. Above them, the planets continue wandering. To understand how strange their movements appear, you only need patience. Watch Mars across many nights, and it usually drifts gradually eastward among the stars. Then its motion slows, it stops, reverses for several weeks, and eventually resumes its previous direction. Today you know this apparent reversal results from the relative motions of Earth and Mars around the Sun. To an ancient observer standing on seemingly motionless ground. However, that explanation is anything but obvious. The puzzle invites geometry. By the 4th century BC, Aristotle developed a broad physical picture that would profoundly influence later European and Islamic thought. Earth occupied the cosmic center, while the heavens belonged to a more perfect and enduring realm. You can understand the appeal. Rocks fall downward, flames rise, the sun crosses the sky, stars circle overhead, while the ground beneath you appears reassuringly stationary. Nothing obvious announces that Earth spins once each day while racing around the sun. Aristotle also argued that nature resisted the existence of empty space. This would later become particularly interesting because black holes eventually force physicists to reconsider basic ideas about space, matter, motion, and even time. But those problems lie far ahead. For now, the cosmos seems structured almost like architecture. Earth occupies the center, while celestial regions extend outward in an ordered hierarchy. The arrangement also carries philosophical comfort. Human beings live in a universe whose geometry appears understandable, even if its ultimate purpose remains mysterious. Not everyone agrees. Around the 3rd century BC, Aristarchus of Samos proposes something startling. He places the sun at the center of planetary motions and allows Earth to move. Imagine hearing that suggestion without modern astronomy. You feel perfectly still. Your cup does not slide from the table. Birds are not permanently blown westward. No tremendous wind announces Earth's rotation. More seriously, the stars show no obvious annual parallax. If Earth changes position by millions of miles during the year, nearby stars should appear to shift against more distant ones. Ancient instruments reveal no such movement. The heliocentric idea therefore creates another uncomfortable possibility. Perhaps the stars are extraordinarily distant. That possibility enlarges the universe dramatically. Scholars still debate many details surrounding Aristarchus's original system because his principal astronomical work describing heliocentrism has not survived intact. Later writers provide much of what you know about his proposal. This is one of history's recurring frustrations. The most interesting manuscript is often missing. Other astronomers concentrate less on cosmic architecture and more on measurement. Hipparchus, working during the 2nd century BC, becomes one of antiquity's most important observational astronomers. You imagine him beneath a clear Mediterranean night, comparing stellar positions with earlier records. There is perhaps a scratch of writing material, the quiet movement of instruments, and the faint smell of lamp oil. The work is slow. Hipparchus is associated with a major star catalogue containing hundreds of stars. He also classified stellar brightness using a magnitude system whose distant descendant astronomers still employ today. Then careful comparison reveals something subtler. The celestial coordinate system itself appears to shift slowly across centuries. Earth's rotational axis gradually changes direction, producing the phenomenon now called the precession of the equinoxes. The sky is not quite as fixed as it seems. That realization contains a lesson that will matter enormously in the history of black holes. Cosmic truths often hide not because nature deliberately conceals them, but because their signals are smaller than a human lifetime. Sometimes you need generations of observations. Centuries later, around the 2nd century AD, Ptolemy brings much of Greek mathematical astronomy into an elaborate predictive framework. You encounter a universe built from circles upon circles. Planets travel along smaller circles whose centers move around larger paths. Additional geometrical devices improve agreement between calculation and observation. To modern ears, this can sound unnecessarily complicated, yet the system should not be dismissed as ancient stubbornness. It predicts planetary positions with useful accuracy. More importantly, it begins with what observers genuinely see. Earth appears stationary. Celestial objects appear to travel around it, and planetary paths contain strange loops requiring explanation. A successful model does not need to resemble modern intuition. It needs to organize evidence available at the time. There is even something faintly familiar here. Future physicists studying black holes will repeatedly encounter mathematical descriptions that seem physically absurd. Some will initially treat troublesome features as artifacts of equations rather than genuine properties of nature. The ancient heavens offer an early warning. Reality does not promise to match intuition. Ptolemy's universe also remains finite and ordered in ways later astronomy will gradually dismantle. The stars appear attached to a distant celestial region rather than scattered through immense three-dimensional space. Their true distances remain unreachable. Without those distances, their physical nature remains obscure. Without stellar physics, nobody can understand how stars generate energy, exhaust fuel, or collapse under gravity. And without gravitational collapse, the path toward black holes remains closed. Still, ancient thinkers occasionally wander surprisingly near questions that will later matter. Greek philosophers debate whether light travels instantaneously or requires time. Atomists speculate about vast spaces and multiple worlds. Others wonder whether the universe might extend beyond the visible celestial structure. These ideas rarely form anything resembling modern astrophysics, yet they demonstrate that the apparently simple night sky has already become intellectually restless. You can feel that restlessness while standing beneath it. A cool breeze moves across the courtyard, somewhere nearby. Sandals scrape softly against stone. Above you, Jupiter shines with the steady brightness of something still mistaken for a wandering celestial light. No telescope reveals its moons. No spectroscopy reveals its atmosphere. No detector measures radiation from invisible objects elsewhere in the galaxy. Human senses remain the primary instruments, yet mathematics has entered the story, and that changes everything. Once you describe the heavens with numbers, predictions can be tested, differences can be noticed, models can compete against measurements rather than surviving only through philosophical elegance. For many centuries, Ptolemy's framework will remain enormously influential. It will be copied, studied, translated, questioned, refined, and eventually challenged. The next transformations will not occur in isolation. Astronomical knowledge will travel through languages, libraries, courts, schools, and observatories stretching across continents. Scholars will inherit ancient measurements and discover that inheritance does not require obedience. They will test the sky again, and while human beings patiently refine their models, unseen black holes continue moving through the Milky Way, bending space-time in a universe whose true architecture remains almost entirely hidden. You still cannot see them, but humanity is learning how to ask better questions. Centuries pass, kingdoms rise and disappear, and the stars continue turning above every border humans draw below them. The astronomical traditions inherited from antiquity do not simply vanish when the political world around the Mediterranean changes. Manuscripts travel, languages shift, and new centers of scholarship emerge farther east. You now enter cities where astronomy becomes part of a remarkable culture of translation, calculation, observation, and debate. Imagine yourself walking through Baghdad during the early 9th century. Evening heat lingers in stone walls, while lamps begin glowing along narrow streets. You smell dust, oil, cooked food, and perhaps the faint sweetness of nearby gardens. Above the rooftops, familiar planets appear. They are the same wandering lights watched by Babylonian observers thousands of years earlier. Yet the intellectual world beneath them has changed dramatically. During the Abbasid period, scholars translated major works of Greek astronomy and mathematics into languages used across the Islamic world. Indian and Persian astronomical traditions also contributed ideas, computational techniques, and observations. Ptolemy became especially important. His mathematical astronomy offered a powerful foundation, but inheritance did not mean unquestioning acceptance. Astronomers examined his parameters, repeated measurements, and identified disagreements between models and observations. That distinction matters. You are not watching ancient knowledge being stored like fragile furniture in a locked room. You are watching scholars use it. In Baghdad, astronomical observations were supported under the Caliph al-Ma'mun during the 9th century. Scholars attempted improved measurements of celestial positions and fundamental astronomical quantities. One ambitious effort involved estimating Earth's circumference. Teams reportedly measured distances across relatively level terrain, while tracking changes in the altitude of celestial reference points. The exact procedures and historical details remain subjects of scholarly reconstruction, but the underlying ambition is unmistakable. Earth itself could be measured. You can imagine the experience of joining such work. Sunlight burns against your face during the day, while dry ground crunches beneath your feet. At night, temperatures fall and instruments are positioned beneath brilliant stars. There are no digital displays. A tiny observational error matters. So does the craftsmanship of every instrument. Astronomers developed and refined devices such as astrolabes, quadrants, and increasingly large angular measuring instruments. These tools helped determine positions, calculate time, and solve practical astronomical problems. The astrolabe becomes particularly widespread. It is beautiful as well as useful, a compact mathematical representation of the sky held between your hands. Metal feels cool beneath your fingers, while engraved lines transform celestial geometry into something almost tangible. There is also a wonderfully human side to such precision. Medieval astronomical texts sometimes contain disagreements about instruments, tables, and numerical parameters that can feel surprisingly familiar. Even people studying the heavens could become irritated by somebody else's calculations. Apparently, infinity does not eliminate professional disagreement. Across centuries, centers of astronomy appear from Baghdad and Damascus to Cairo, Persia, Central Asia, and the Iberian Peninsula. The exact network changes with political circumstances, patronage, and individual scholars. By the 10th century, Abd al-Rahman al-Sufi carefully described stars and constellations while revising information inherited from Ptolemy. His work included observations of what you now recognize as the Andromeda Galaxy, described as a small cloud-like feature. Think about that for a moment. You look toward a faint patch of light without knowing that it contains hundreds of billions of stars. The photons reaching your eyes began traveling roughly 2.5 million years earlier. Humanity has noticed another galaxy. It simply does not know what it is. That small cloud will eventually become part of a much larger transformation. Astronomers will learn that the Milky Way is not the entire universe, and black holes will later appear near the centers of enormous galaxies. For now, the scale remains hidden. Other scholars confront difficulties within Ptolemaic astronomy itself. Ibn al-Haytham, known especially for his major work on optics, criticized aspects of Ptolemy's physical models. His investigations of light also contributed to a broader transformation in understanding vision and observation. This is important for your journey. Black holes are defined partly through their relationship with light. Yet before anyone can imagine light failing to escape gravity, humanity must understand light as a physical phenomenon, rather than simply a mysterious ingredient of sight. Optics therefore becomes quietly relevant. You might sit near a small opening in a darkened room and watch an inverted outdoor image appear on the opposite surface. Experiments involving light, reflection, and vision encourage scholars to treat observation itself as something that can be investigated. Nature becomes interrogable. By the 13th century, major observatories provide increasingly sophisticated environments for astronomical measurement. The Maraga Observatory in Persia becomes especially significant. There, astronomers including Nasir al-Din al-Tusi develop mathematical techniques capable of modifying problematic features of Ptolemaic planetary models. One construction, later called the Tusi couple, combines circular motions to generate apparent linear movement. It sounds technical, and it is, but the deeper point is gentle and simple. Scholars are discovering that an inherited mathematical system can be adjusted without abandoning mathematical astronomy itself. Later, during the 15th century, Ulugh Beg establishes a major observatory at Samarkand. You can imagine approaching its enormous instruments under a cold, clear Central Asian sky. Stone and masonry replace the small handheld scale of earlier devices. One immense meridian instrument allows exceptionally precise angular measurements. Ulugh Beg and his collaborators produce a celebrated star catalogue based substantially on new observations. Their measurements become among the finest achievements of naked-eye astronomy. The telescope still has not arrived. Human vision is being stretched through architecture. Meanwhile, astronomy also flourishes in other regions and traditions, and historians continue examining how ideas moved between scholars separated by geography, religion, and language. Exactly how particular mathematical techniques influenced later European astronomy can be difficult to establish. Similar geometrical devices sometimes appear across traditions without surviving documents showing every step of transmission. Historical knowledge has horizons too. You can see evidence approaching them, then lose sight of what happened beyond. Yet the larger pattern is clear. Astronomy has become increasingly observational, mathematical, and international. Ancient models remain powerful, but they are no longer untouched monuments. Measurements accumulate. Small discrepancies accumulate with them by the late medieval period. European scholars also have growing access to astronomical texts transmitted through translation networks. Universities teach mathematical astronomy, while calendars and planetary predictions maintain practical importance. The cosmos still appears largely geocentric, but confidence in its machinery is becoming less effortless. You stand outside once more as the night deepens. Somewhere nearby, paper rustles beneath a scholar's hand. Metal instruments cool under the open sky, and distant voices soften as calculations continue by lamplight. Above you, the stars remain silent. Among them are stellar systems containing invisible black holes. At the centers of distant galaxies, enormous black holes may already possess masses millions or billions of times greater than the Sun. No medieval observer can know this. Still, something essential has changed since the earliest sky watchers. Humanity now possesses a growing tradition of checking inherited ideas against the heavens themselves. Soon, one European astronomer will rearrange the planets around the Sun. Another will measure their positions with extraordinary precision. A third will discover that their paths are not perfect circles. Then a small tube of glass will be pointed upward, and the old sky will never look quite the same again. By the 16th century, the old celestial machinery still turns, but its comfortable certainty has begun to loosen. You can feel the change before you can see it. Printing presses clatter inside European workshops. Paper carries calculations farther and faster than handwritten manuscripts once could. Ships cross unfamiliar oceans, while map makers redraw coastlines that educated Europeans had never imagined so precisely. The heavens are about to be redrawn too. In 1543, as Nicholas Copernicus lay near the end of his life, his great astronomical work appeared in print. Its central arrangement placed the Sun near the center of planetary motions and allowed Earth to become a moving world. You hold that idea carefully. The paper feels rough beneath your fingers, carrying the smell of ink and the faint mustiness of a newly bound volume. Outside, nothing seems different. Earth still feels perfectly motionless. That is the problem. Copernicus has not suddenly produced overwhelming observational proof that Earth moves. His system offers mathematical and conceptual advantages. including a natural explanation for the strange backward loops of planets. Imagine Earth and Mars moving around the Sun at different speeds, as faster-moving Earth overtakes Mars. The distant planet temporarily appears to move backward against the stars. No actual reversal is required. The strange loop becomes perspective. Yet Copernicus retains circular motions and mathematical devices inherited from older astronomy. His cosmos is revolutionary, but not entirely modern. Historians continue discussing precisely what mixture of physical conviction, mathematical elegance, and philosophical preference motivated his heliocentric commitment. Historical revolutions are rarely as tidy as later textbooks make them appear. Even revolutions keep old furniture. Still, Earth has been displaced. That conceptual movement matters for the future history of black holes because it weakens an ancient distinction between terrestrial and celestial physics. If Earth is another planet, perhaps the heavens are not a separate kind of reality. The next observer makes the evidence far more precise. Tycho Brahe constructs an extraordinary program of naked-eye astronomical measurement during the late 16th century, before telescopes become practical astronomical instruments. He pushes positional observation remarkably close to its limits. You arrive at his island observatory of Uraniborg on Hven. Wind carries the smell of seawater across the island. Brass instruments catch weak light while assistants move between observing stations, recording numbers beneath cold northern skies. Tycho's instruments are enormous. Large quadrants and sextants provide stability and carefully divided angular scales. His observations of planetary positions become substantially more accurate than much earlier European data. Then the heavens misbehave. In 1572, Tycho observes a brilliant new star in the constellation Cassiopeia. Today, you identify it as a supernova, the catastrophic explosion of a star. To Tycho, its location is crucial. He finds no detectable parallax indicating that the object belongs to Earth's atmosphere or nearby celestial region. It appears among the supposedly unchanging stars. Something has changed in the heavens. A few years later, the great comet of 1577 creates another difficulty. Tycho's measurements indicate that it travels through regions where solid celestial spheres were traditionally imagined. The old architecture begins cracking. Tycho does not accept Copernicus's fully moving Earth. Instead, he develops a hybrid arrangement in which planets orbit the Sun, while the Sun moves around stationary Earth. Again, this deserves sympathy rather than ridicule. No convincing physical explanation yet exists for why a massive Earth should move. Stellar parallax remains undetected. Several models can still reproduce important observations. Evidence has not finished speaking. After Tycho's death in 1601, Johannes Kepler gains access to his precious planetary measurements. Mars becomes the troublemaker. Kepler tries repeatedly to fit its orbit using combinations of circular motion. A discrepancy of roughly 8 arc-minutes refuses to disappear. 8 arc-minutes is a tiny angle. You could easily imagine ignoring it. Kepler does not. He trusts Tycho's measurements enough to conclude that the model must change. Eventually, he discovers that planets travel around the Sun in ellipses rather than perfect circles. A small observational disagreement breaks an ancient ideal. This is one of astronomy's recurring patterns. Tiny discrepancies can open enormous doors. Centuries later, strange stellar motions and unexplained radiation will similarly reveal objects nobody can see directly. But first, humanity needs better eyes. Around 1608, spectacle makers in the Netherlands develop instruments capable of making distant objects appear closer. News of these devices spreads quickly. In 1609, Galileo Galilei constructs improved versions and turns them toward the heavens. You raise one of these early telescopes toward the moon. The instrument is awkward by modern standards. The field of view is narrow. Glass imperfections distort the image, and holding the tube steady requires patience. Then the moon enters view. Its surface is not perfectly smooth. Light and shadow reveal irregular terrain that Galileo interprets as mountains and depressions. The supposedly flawless celestial world suddenly resembles rough landscapes familiar on Earth. Then you turn toward Jupiter. In January 1610, Galileo observes small points of light near the planet. Their positions change from night to night. Eventually, the pattern becomes unmistakable. 4 bodies orbit Jupiter. Not everything revolves around Earth. The discovery does not instantly prove heliocentrism, but it destroys one simple objection to it. A moving celestial body can carry orbiting companions. Galileo observes phases of Venus as well. The full sequence is incompatible with the traditional Ptolemaic arrangement and supports models in which Venus circles the Sun. The telescope has changed the argument. You can almost hear the excitement hidden beneath the quiet observing room. Wood creaks, clothing brushes against the instrument. Cold air touches your hands, while Jupiter trembles in imperfect glass. There is also controversy. Early telescopic observations are difficult to verify because instruments vary in quality, and inexperienced observers sometimes struggle to recognize what Galileo describes. A quirky story from this period captures the problem beautifully. Some scholars reportedly distrusted telescopic evidence itself, treating the unfamiliar instrument as potentially deceptive. It is not entirely unreasonable. Whenever a new instrument reveals something astonishing, you first need confidence that the instrument is not creating the astonishing thing. That problem will return. Radio telescopes, X-ray detectors, gravitational wave observatories, and horizon-scale imaging will all require extraordinary calibration before scientists trust what cannot be checked with ordinary eyes. For now, telescopes continue improving. The universe fills with previously invisible stars. Saturn looks strange and complicated. Sunspots cross the solar surface, further challenging the idea of celestial perfection. The sky becomes physical. That transformation brings humanity closer to black holes, even though nobody yet imagines them clearly. Stars must eventually become physical objects, governed by natural laws rather than eternal points embedded in a celestial structure. You step outside as dawn approaches. The telescope tube is cold beneath your hand. Jupiter fades into the brightening sky, carrying its newly discovered moons with it. Earth now belongs to a planetary system. The heavens can change, and the same physics may reach from the ground beneath your feet to the most distant lights above you. One final ingredient is missing. Someone must explain the force that holds this moving universe together. The moving universe now needs something powerful enough to keep it from flying apart. By the middle of the 17th century, you inherit a cosmos transformed by observation. Earth circles the sun. Planetary paths can be described by Kepler's laws, and telescopes reveal celestial bodies with physical features. Yet one question remains stubbornly open. Why do planets move this way? In 1665, plague spreads through England. Closing the University of Cambridge, and sending a young Isaac Newton back to the countryside. He spends much of the following period at Woolsthorpe Manor, away from ordinary university life. You arrive there beneath a quieter sky. Rain darkens the fields. Damp earth carries its heavy smell through the cool air. While timber creaks inside the house during long evenings, Newton thinks about motion, mathematics, optics, and gravity. The famous falling apple enters the story here. Later accounts, including recollections associated with Newton himself, describe an apple-inspiring reflection about gravity. The fruit probably did not strike him dramatically on the head, despite generations of cheerful illustrations suggesting otherwise. History occasionally prefers better aim. The important question is not why an apple falls. It is how far gravity reaches. You watch the moon moving across the night sky. If gravity pulls objects downward near Earth's surface, perhaps the same attraction extends all the way to the moon. Then an extraordinary possibility appears. The moon is falling too. It continually falls toward Earth while its sideways motion carries it forward, producing an orbit rather than a collision. The distinction between terrestrial and celestial motion begins disappearing. By 1687, Newton publishes his great mathematical work on motion and gravitation. His universal law describes gravitational attraction as increasing with mass and weakening with the square of distance. You can now connect the apple, moon, planets, and comets through the same physical principle. This is a profound simplification. There is no separate gravity for heaven. A planet does not need an invisible celestial sphere carrying it around the sun. Motion can continue naturally while gravitational attraction continuously bends the path. Kepler's mathematical patterns acquire a physical foundation. You can almost feel the universe becoming more unified. Stand beside a cold window at night and look toward the moon. The same tendency that gives your body weight also helps shape that distant orbit. Gravity crosses empty space. Newton himself remains cautious about explaining exactly how gravitational influence operates across distance. Scholars have long discussed how his theological, philosophical, and mathematical views shaped his interpretation of the force. The equations work even while deeper questions remain. That pattern will become familiar. Physics often learns how nature behaves before understanding what that behavior ultimately means. Newtonian gravity also gives astronomers a remarkable new ability. Invisible objects can be inferred from their gravitational influence on visible ones. You have already glimpsed the dramatic 19th century example of Neptune. Long before that discovery, however, Newtonian mechanics allows increasingly precise calculations of planetary and cometary motion. Edmund Halley applies the new framework to comets. A bright comet observed in 1682 appears connected with earlier recorded visitors. Halley predicts that it will return around 1758. He does not live to see the prediction succeed. The comet returns anyway. Nature is wonderfully indifferent to whether the person who calculated something remains available for congratulations. This predictive success strengthens confidence in universal gravitation. The heavens are no longer merely mapped. Their future motions can be calculated, but gravity contains a darker implication. Consider escape. Throw a stone upward, and it rises briefly before gravity pulls it back. Throw it faster, and it travels farther before returning. Imagine increasing the speed. Eventually, in Newtonian physics, an object could move fast enough to escape Earth's gravitational attraction permanently. This threshold becomes known as escape velocity. Earth's escape velocity is roughly 11 kilometers per second. The Moon's is lower because the Moon is less massive. The Sun's surface escape velocity is much higher, reaching hundreds of kilometers per second. Now you can ask an unsettling question. What happens if an object becomes extremely massive while remaining extremely compact? Its escape velocity rises. At this stage, nobody has yet combined the idea with a mature physical understanding of light. Newton himself experiments extensively with optics and argues for a particle-like conception of light. Other thinkers favor wave descriptions. The nature of light becomes one of physics' longest conversations. You enter a darkened room where a narrow beam of sunlight passes through a glass prism. Dust floats through the beam while colors spread across a nearby surface. Red merges toward orange, yellow, green, blue, and violet. Newton demonstrates that white light contains different colors rather than acquiring them simply through interaction with the prism. This matters far beyond beautiful experiments. Centuries later, astronomers will separate starlight into spectra and learn the chemical composition, temperature, and motion of distant stars. Eventually, they will examine glowing matter falling toward black holes. Light will become evidence. For now, however, gravity and light remain separate puzzles. You can sense how close the ingredients are becoming. Universal gravity exists. Escape velocity can be calculated. Light is increasingly treated as something physical. Stars are being studied through telescopes. Yet the concept of a black hole still requires one more intellectual leap. Someone must imagine a star whose gravity becomes so strong that even light cannot escape. There is an important complication. Within Newton's framework, light and gravity do not interact in the modern relativistic sense. Different 18th century thinkers will therefore reason from assumptions that later physics modifies dramatically. Their dark objects will not be modern black holes. Still, the resemblance will be remarkable. Meanwhile, telescopes grow longer and observatories multiply. Astronomers chart planetary positions, discover comets, measure moons, and search for stellar parallax. Ordinary people can also encounter astronomy differently now. Printed almanacs carry celestial predictions into homes and workshops. Eclipses and comet appearances become events that can be anticipated rather than merely feared. The sky is becoming predictable, and predictability creates confidence. If gravity can explain planetary motion, perhaps the same equations can be pushed into conditions nobody has observed. That is where theoretical physics begins becoming wonderfully dangerous. You no longer need nature to place an object directly before you. Mathematics allows you to ask what could exist if known laws are taken seriously. Some answers will sound absurd. A star that cannot shine will be one of them. As the 18th century approaches its later decades, improved astronomy begins revealing a universe filled with more stars than previous generations imagined. Their distances remain uncertain, and their internal workings remain completely mysterious. Still, they are increasingly treated as physical suns. You stand outside beneath a cold English night. Frost forms along grass near your boots. Your breath briefly clouds the air, while stars glitter with the sharpness of distant ice. Gravity connects you to every one of them. Somewhere among those points, massive stars are already approaching the ends of their lives. Elsewhere, black holes formed long before humanity existed continue silently bending space-time. Newton has not discovered them. He has done something more fundamental. He has given future thinkers a mathematical language strong enough to imagine that darkness might possess gravity. Soon, someone will use it. By the late 18th century, gravity has become something you can calculate rather than merely feel. The transformation is subtle but profound. Newton's equations have survived demanding tests, while astronomers increasingly treat the heavens as a physical system governed by laws shared with Earth. Now imagination can follow mathematics into places no telescope has reached. In 1783, an English natural philosopher named John Michell presents one of the strangest astronomical ideas of his century. His argument appears before the Royal Society through a paper communicated by Henry Cavendish. You might picture Michell working beneath candlelight in the quiet English countryside. Paper rests beneath his hand. Wax and smoke scent the room, and winter air presses cold against the window glass. His question sounds almost modern. Could a star be invisible because its gravity prevents its light from escaping? To reach that question, you begin with Newtonian escape velocity. Imagine standing on a world and throwing a stone upward. A gentle throw returns quickly. A stronger throw climbs higher before falling. Increase the speed enough, and the stone escapes permanently. Now imagine a much more massive body. Its gravitational attraction is stronger, so the required escape velocity rises. Compress that mass into a sufficiently small region, and the required speed becomes greater still. Michell pushes the reasoning toward light. If light consists of particles affected by gravity, as some Newtonian ideas suggested, perhaps a sufficiently massive compact star could prevent those particles from escaping. The star would disappear, not because it had ceased existing, but because its light could never reach your eyes. Michell estimates that a body with the sun's density and roughly 500 times its diameter could possess an escape velocity comparable with the known speed of light. His object becomes what later writers call a dark star. It is not yet a black hole. The distinction matters because Michell works within Newtonian physics, where space and time remain fixed backgrounds. Modern black holes arise from general relativity, where gravity changes the geometry of space-time itself. Still, you have crossed an extraordinary conceptual threshold. Darkness can now contain an object. Michell goes even further. If such a star cannot be seen directly, perhaps you could detect its gravitational influence on a visible companion. A luminous star might orbit something hidden, betraying the invisible body's presence through motion. This suggestion is astonishingly forward-looking. Nearly 2 centuries later, astronomers will identify strong black hole candidates using essentially that strategy. They will watch visible stars orbit unseen companions and calculate the hidden masses. Nature leaves fingerprints without showing its hand. Michell's proposal attracts some attention, although historians still examine how seriously and widely his dark stars were discussed among contemporary natural philosophers. The idea never becomes a central astronomical research program. There is little observational reason for it to do so. No one understands how stars produce light. No one knows their true life cycles. There is no theory of stellar collapse capable of naturally creating Michell's compact objects. The mathematics permits them, but nature has not yet supplied a convincing story for making them. Across the English Channel, another remarkable thinker reaches similar territory. Pierre-Simon Laplace becomes one of the great mathematical physicists of his age. During the 1790s, he discusses the possibility that extremely massive stars might possess gravity strong enough to prevent their light from reaching observers. You can imagine the intellectual atmosphere surrounding such calculations. Mechanical explanations appear increasingly powerful. Planetary motions submit to mathematics. Comets return when predicted. The universe seems almost like an immense clock whose future can, at least in principle, be calculated. Dark stars fit surprisingly well within that worldview. They are extreme machines. Nothing mystical is required. You simply increase mass, calculate escape velocity, and discover that light cannot get away. There is even a mildly amusing consequence. An invisible star might be sitting somewhere in the sky, while astronomers carefully catalogue an apparently empty patch around it. The greatest object in the neighborhood could be the one missing from the catalogue. Yet the dark star idea begins fading during the 19th century. One reason involves changing theories of light. Experiments increasingly demonstrate wave behavior. Thomas Young's interference work and later developments strengthen the wave description, making the old Newtonian picture of gravitationally slowed light particles much less straightforward. If light behaves as a wave traveling through space, what exactly does escape velocity mean for it? The old argument loses its foundation. This does not mean scientists have proved that extremely compact invisible objects cannot exist. Rather, the particular theoretical path leading toward them has become uncertain. Science sometimes abandons a correct destination because the road used to reach it was wrong. There is another difficulty. The physical nature of stars remains mysterious. When you look through an 18th-century telescope, a star remains essentially a point of light. Even large instruments cannot show ordinary stellar surfaces as resolved disks. Distances are poorly known. Without reliable distances, true luminosities remain difficult to determine. Without spectroscopy, stellar chemistry remains hidden. Without nuclear physics, their energy source is unimaginable. The sun itself poses a puzzle. If it burns like ordinary fuel, geological evidence eventually suggests it cannot remain luminous for the immense spans of time Earth seems to require. Some 19th-century scientists explore gravitational contraction as a possible energy source. That mechanism can provide substantial energy, but not enough for the sun's actual age. The answer waits inside atomic nuclei. Meanwhile, telescopes are changing dramatically. William Herschel builds increasingly powerful reflecting instruments and conducts enormous surveys of the heavens. In 1781, he discovers Uranus, the first planet recognized in recorded history through telescopic observation. The known solar system expands. Herschel also counts stars in different directions, attempting to infer the structure of the Milky Way. His resulting model is limited by dust and observational selection, problems he cannot fully recognize. Still, the ambition is remarkable. You are no longer merely mapping a celestial sphere. You're trying to determine the shape of a galaxy from inside it. On clear nights, Herschel's telescopes gather faint light from nebulae, double stars, clusters, and remote celestial structures. Cold air settles around the instruments, while metal and wood become uncomfortable beneath your hands. The smell of damp grass mixes with lamp smoke. Occasionally, an assistant records observations while the telescope continues sweeping. The universe grows crowded. Herschel's observations of double stars become especially important because some pairs prove to be physically associated rather than accidental alignments. Stars orbit other stars. Newtonian gravity operates beyond the solar system. That evidence strengthens a principle Michel had already assumed. The same gravity governing planets also governs distant suns. And if visible stars can orbit each other, perhaps visible stars can orbit invisible companions too. The idea waits quietly. Humanity still lacks the instruments needed to find the right systems and the physics needed to understand what those hidden companions might be. Throughout the 19th century, dark stars largely retreat from astronomical conversation. But the universe itself remains unchanged. Black holes continue forming from massive stars. Matter spirals toward them, heating to extraordinary temperatures. Supermassive black holes inhabit galactic centers. Their existence does not depend upon whether anyone believes the equations. You stand beneath the night sky again, but now it feels subtly different. Every bright star carries physical questions. How far away is it? What is it made from? Why does it shine? How massive is it? Soon, astronomers will learn to extract answers from the light itself. They will split starlight into colors, photograph the heavens, measure stellar motions, and discover that stars have histories. Once stars can be born, they can also die. And when physicists finally understand how the most massive stars die, Michel's forgotten darkness will return in a form far stranger than he could have imagined. Through the 19th century, the heavens begin surrendering a secret that earlier astronomers could scarcely have imagined. Starlight contains information. For thousands of years, you could record where a star appeared, how brightly it shone, and how it moved. Now you begin learning what that distant point of light is physically made from. The change starts with something beautifully simple. You pass light through a prism. Newton had already separated sunlight into its familiar spectrum during the 17th century. Later observers noticed something more delicate within those colors. In 1802, William Hyde Wollaston reports dark features crossing the solar spectrum. Joseph von Fraunhofer later studies these lines systematically and maps hundreds with remarkable precision. You can picture Fraunhofer working with carefully constructed optical equipment. Glass feels smooth and cold beneath your fingers. The room carries the smells of metal, oil, and workshop dust. Sunlight enters through a narrow opening. Colors spread before you. Across them lie thin, dark lines. At first, they resemble imperfections. They are anything but imperfections. During the 19th century, laboratory experiments gradually connect specific spectral patterns with particular chemical elements. Gustav Kirchhoff and Robert Bunsen make especially important contributions during the 1850s and 1860s. Heat an element, and it produces characteristic spectral lines. Those lines become fingerprints. Suddenly, you possess a method for touching the stars without traveling anywhere near them. The implications are enormous. For centuries, philosophers had wondered whether celestial matter might be fundamentally different from earthly material. Spectroscopy shows that familiar elements exist beyond Earth. Sodium leaves recognizable signatures. Hydrogen does too. The heavens and earth share chemistry. A frequently repeated philosophical claim had suggested humanity might never know what stars are made from. Spectroscopy responds with the scientific equivalent of an unexpectedly polite correction. The universe has mailed its ingredients to you in light. This technique eventually transforms astronomy into astrophysics. You are no longer satisfied with positions. You want temperatures, compositions, velocities, magnetic fields, and physical mechanisms. Photography expands that transformation. Human eyes are wonderful, but they tire. Photographic plates can collect faint light over extended exposures and preserve observations for later examination. The night sky becomes an archive. You imagine an observatory dome turning slowly beneath a dark 19th century sky. Clockwork mechanisms tick quietly. Cold metal presses against your hand, while chemicals from photographic preparation leave sharp smells nearby. A telescope tracks the stars. Minutes become hours. Faint objects gradually record themselves. Some structures, invisible during ordinary visual observation, emerge through long exposure. Astronomy begins extending human perception beyond what the eye can immediately detect. That principle will become essential for black holes. You cannot see a black hole directly in the ordinary sense, but you can build instruments sensitive to what happens around it. Before that becomes possible, however, astronomers need to understand stars. Distances provide another crucial step. In 1838, Friedrich Bessel announces a successful measurement of stellar parallax for the star 61 Cygni. Other astronomers achieve comparable measurements around the same period. The effect is tiny. As Earth travels around the Sun, a nearby star appears to shift slightly against more distant stars. Aristarchus had faced the absence of detectable parallax more than 2,000 years earlier. Now instruments finally become precise enough. The stars are extremely far away. That ancient possibility becomes measured reality. Once you know distance, apparent brightness can be converted into intrinsic luminosity. Stars that look faint may simply be remote, while others truly produce less light. The celestial landscape gains depth. William Herschel's earlier attempts to map the Milky Way had assumed that telescopes could penetrate stellar space more evenly than they actually could. Interstellar dust hides enormous regions, complicating the picture. Astronomers still debate exactly how 19th century observers interpreted certain nebulae because observational categories changed as instruments improved. A cloudy patch might represent gas, unresolved stars, or something much farther away. The universe remains deceptive. Some nebulae become especially intriguing. Improved spectroscopy reveals that certain examples produce emission lines associated with glowing gas. Others show spectra more like collections of stars. The old category of nebula begins splitting into physically different objects. Meanwhile, stellar spectra themselves reveal motion through the Doppler effect. If spectral features shift toward longer wavelengths, an object may be moving away along your line of sight. Shifts toward shorter wavelengths can indicate approach. Now the sky has radial velocity. You can measure movement that your eyes cannot perceive. This will later become one of the methods used to weigh unseen companions. Suppose a visible star moves repeatedly toward you and away from you. Perhaps another object is pulling it around a shared center of mass. You might never see the companion. Its gravity writes a rhythm into the visible star's spectrum. John Michel would have recognized the logic. Yet black holes remain outside mainstream 19th century astronomy because stellar evolution is still poorly understood. Physicists know gravity can release energy when matter contracts. Lord Kelvin and Hermann von Helmholtz explore gravitational contraction as an explanation for the sun's luminosity. The mechanism seems plausible. As the sun slowly contracts, gravitational energy becomes heat and radiation. But the numbers create trouble. The resulting lifetime is far shorter than the enormous geological timescales increasingly suggested by studies of Earth. Something is missing inside stars. Radioactivity. discovered near the century's end, complicates older estimates of Earth's age. Nuclear physics will eventually reveal the deeper stellar answer. Stars shine through fusion. That discovery still waits in the 20th century. Another important development comes from the strange behavior of compact stellar remnants. In 1862, observers confirm a faint companion to Sirius that had been predicted from irregularities in the bright star's motion. Sirius B is extraordinarily dim compared with Sirius A. Later measurements show that it is a white dwarf. Imagine compressing roughly stellar-scale mass into an object comparable in size with Earth. The density is astonishing. A teaspoon of white dwarf material would possess a mass measured in tons under earthly gravity, although extracting such a teaspoon would be a rather ambitious laboratory procedure. Nature can make matter far denser than everyday experience suggests. That realization brings you closer to black holes. If stars can become compact remnants, perhaps gravity can produce objects stranger than ordinary stars. Still, white dwarfs are not black holes. Some physical mechanism prevents their collapse. Understanding that mechanism will require quantum physics, another revolution waiting just beyond the 19th century. At the same time, astronomers begin realizing that the Milky Way itself may not define the entire cosmos. Debate continues over spiral nebulae. Are they structures within our stellar system, or enormous distant systems comparable with the Milky Way? The question will survive into the 20th century. You look upward through increasingly sophisticated instruments. The sky that ancient observers saw as a patterned dome has become a three-dimensional physical environment. Stars have chemical compositions. They move through space. Some orbit unseen companions. Some become remarkably dense. Yet humanity still lacks a theory capable of describing gravity under truly extreme conditions. Newton's framework has carried astronomy astonishingly far, from falling objects to binary stars. Soon, however, scientists will discover situations where its assumptions cannot survive. Space itself will become flexible. Time will cease being universal. Gravity will no longer be treated simply as a force pulling across an empty stage. And inside the equations of that new universe, the forgotten dark star will return. This time, darkness will not result merely from insufficient escape speed. It will become a boundary in space-time. At the beginning of the 20th century, the universe still appears to rest upon the sturdy foundations Newton provided. Those foundations have explained falling bodies, planetary orbits, comets, tides, and the motions of binary stars. They have survived for more than 2 centuries. Then small difficulties begin gathering around the edges. Mercury provides one of them. Its orbit slowly rotates through space, producing a shift in the location of its closest approach to the Sun. Most of that motion can be explained through Newtonian gravitational interactions with other planets. A small remainder persists. The discrepancy is tiny, amounting to roughly 43 arcseconds per century. You could almost lose it inside observational uncertainty. Astronomers do not. Some speculate about an undiscovered planet inside Mercury's orbit. It receives the proposed name Vulcan, and observers occasionally report possible sightings. The hypothetical world becomes surprisingly popular. Unfortunately for Vulcan, mathematics will eventually remove it from the solar system without the courtesy of allowing anyone to visit. The deeper problem lies with gravity itself. In 1905, Albert Einstein publishes his special theory of relativity. Space and time cease behaving as separate universal backgrounds. while the speed of light acquires a fundamental role in physics. You now inhabit a stranger universe. Observers moving differently can disagree about elapsed time and measured distance, yet the physical laws remain consistent, and the speed of light in vacuum remains the same. Gravity is not included fully yet. Einstein spends the following decade trying to bring it into this new framework. You can imagine him working through pages of equations, paper shifting beneath his hands, while tobacco smoke and city air linger around European rooms and offices. The problem is difficult. Newtonian gravity acts across distance in a way that sits uneasily beside relativity. Einstein needs another description. The crucial insight develops from the equivalence between gravitational effects and acceleration. Imagine standing inside a sealed elevator. If the elevator accelerates upward in empty space, your feet press against the floor, without seeing outside. You might interpret that sensation as gravity. Now imagine falling freely. For a brief interval, you feel weightless. Gravity begins looking less like an ordinary force and more like something connected with the structure of motion itself. By 1915, Einstein presents the completed field equations of general relativity. Matter and energy influence space-time geometry. That geometry influences how matter moves. You can picture space-time as a stage that no longer remains rigid while the actors perform. The stage itself bends according to what stands upon it. The analogy is imperfect, but useful. A planet following an orbit is not simply being pulled through fixed space. It follows the natural geometry of curved space-time surrounding the Sun. Mercury's unexplained orbital shift now emerges naturally. No hidden planet is required. General relativity accounts for the mysterious additional precession with remarkable accuracy. The old discrepancy becomes evidence. Then comes another test. Einstein's theory predicts that light passing near a massive body should change direction because space-time itself is curved. A total solar eclipse offers an opportunity to measure the effect. In 1919, expeditions led by Arthur Eddington and Frank Dyson observed stars near the eclipsed Sun from locations including Principe and Sobral. You can imagine the atmosphere. Tropical humidity clings to clothing. Equipment must be transported and aligned carefully. Clouds threaten observations that depend on a few precious minutes of darkness. Then the moon covers the Sun. Stars appear around the black solar disk. Measurements reported afterward support Einstein's prediction and help transform him into an international celebrity. Historians and physicists have subsequently examined the quality and interpretation of those eclipse measurements in considerable detail. The broad relativistic prediction has since been confirmed far more precisely by later observations. But in 1919, the symbolism is irresistible. Light bends around gravity. Now return to the old idea of a dark star. Michel had imagined light particles struggling against Newtonian attraction. Einstein's universe changes the question completely. Light follows paths through curved space-time. If space-time becomes sufficiently distorted, perhaps something far stranger than a Newtonian dark star can exist. Remarkably, the mathematical doorway appears almost immediately. Only weeks after Einstein presents his final field equations, Karl Schwarzschild finds an exact solution describing space-time outside a spherical, non-rotating mass. Schwarzschild produces this work during the First World War. You might imagine the contrast. Artillery sounds across distant landscapes, while one man studies equations describing gravity around idealized stars. Mud, cold air, military routine, and cosmic geometry occupy the same historical moment. His solution contains a peculiar radius. In modern terminology, the Schwarzschild radius for a mass m is given by 2gm_c2. For the Sun, that radius is roughly 3 kilometers. The actual Sun is vastly larger, so nothing resembling a horizon surrounds it. But imagine compressing the Sun. Smaller, denser, keep squeezing until its entire mass lies within roughly 3 kilometers. The geometry changes dramatically. In Schwarzschild's original coordinates, certain mathematical quantities appear badly behaved at this radius. Another apparent problem occurs at the center. What do these strange features mean? At first, nobody has a clear physical answer. Einstein himself does not immediately interpret the solution as evidence that real stars can become black holes. The modern concept of an event horizon has not yet fully emerged. The mathematics is ahead of intuition. Some physicists suspect the troublesome radius may simply represent a coordinate problem, rather like a map behaving strangely at a pole. That suspicion eventually proves partly correct. The horizon itself is not a physical singularity for a sufficiently large, freely falling observer. Different coordinates can describe passage across it smoothly. The center is another matter. There, classical general relativity predicts a genuine singularity under idealized conditions. You cannot yet know whether nature permits such objects. The equations merely whisper that something extraordinary may happen when mass becomes compact enough. And equations alone are not sufficient. A star must somehow reach this condition. That requires understanding stellar interiors. During these same decades, quantum theory is beginning its own revolution. Matter behaves in ways classical physics never anticipated. Atoms acquire quantum structure. Electrons obey unfamiliar rules. Eventually, these principles will explain why white dwarfs resist gravitational collapse. But they will also reveal a limit, make a stellar remnant sufficiently massive, and even quantum pressure may fail. For now, you stand at the edge of that discovery. Outside, the night remains deceptively peaceful. A cold breeze moves across the observatory grounds, and distant stars tremble through Earth's atmosphere. Some of those stars are massive. Some will collapse. General relativity has quietly prepared a destination for them, although few physicists yet believe nature will actually travel there. The impossible object has returned to mathematics. The next question is whether a real star can fall far enough to become one. The equations now contain a doorway into extreme gravity, but nobody yet knows whether a dying star can actually pass through it. To answer that question, you must leave the geometry of empty space-time and travel inside the stars themselves. During the early 20th century, that interior is finally becoming understandable. Astronomers have learned that stars differ enormously in temperature, luminosity, and mass. Spectroscopy has turned their light into physical evidence, while atomic physics begins explaining the fingerprints hidden within stellar spectra. Then nuclear physics reveals the source of stellar power, deep inside a star like the Sun. Immense pressure and temperature allow hydrogen nuclei eventually to become helium through fusion processes. A small amount of mass becomes energy. The mystery of stellar longevity begins to dissolve. You can imagine descending toward the solar interior, although no physical traveler could survive the journey. Light becomes trapped in dense plasma. Temperatures climb into millions of degrees, and pressure reaches values beyond ordinary experience. Yet every star carries a quiet conflict. Gravity pulls inward. Pressure pushes outward. For most of a star's active lifetime, These tendencies remain approximately balanced. The arrangement is called hydrostatic equilibrium. It sounds peaceful. It is really a permanent negotiation. Eventually, available nuclear fuel changes, and the internal structure changes with it. What happens next depends strongly upon stellar mass. The smallest stars evolve slowly. Stars resembling the Sun eventually leave compact remnants called white dwarfs. These objects contain extraordinary densities, yet they do not continue collapsing under ordinary circumstances. Quantum mechanics provides the resistance. Electrons obey the Pauli exclusion principle, which prevents identical fermions from occupying the same quantum state under extreme compression. This produces electron degeneracy pressure. Gravity has met a new opponent. Then, in 1930, a 19-year-old Subramanian Chandrasekhar travels by ship from India toward England. You join him somewhere across the long sea passage. The ship vibrates softly beneath your feet. Salt air enters through openings, mixing with engine smells and the damp scent of ocean weather. Chandrasekhar spends part of the voyage thinking about white dwarfs. He combines quantum mechanics with special relativity and realizes that electron degeneracy pressure has a limit. As a white dwarf becomes increasingly massive, its electrons must occupy states involving greater momenta. Relativistic effects change the relationship between pressure and density. Eventually, gravity wins. Chandrasekhar calculates that a white dwarf cannot remain stable above a mass of roughly 1.4 times the Sun's mass, with the exact value depending on composition and physical assumptions. Today, this is called the Chandrasekhar limit. At the time, its implications are disturbing. If a sufficiently massive stellar core cannot become a stable white dwarf, what happens to it? Arthur Eddington, one of the most respected astrophysicists of the era, strongly resists the conclusion that stellar matter might continue toward extreme collapse. The disagreement becomes famous. Historians have examined both its scientific and personal dimensions, and the episode is sometimes simplified into a cleaner confrontation than the surviving historical context deserves. Still, the fundamental question remains: can nature collapse a star beyond familiar matter? Another possibility soon appears. In 1932, James Chadwick announces the discovery of the neutron. Only 2 years later, Walter Baade and Fritz Zwicky propose that supernova explosions might create extraordinarily compact neutron stars. The concept is astonishing. Instead of an Earth-sized white dwarf, imagine compressing stellar-scale mass into a sphere only tens of kilometers across. The resulting density approaches that of atomic nuclei. A spoonful of such matter would have a mass measured in hundreds of millions or billions of tons, depending on precisely what comparison you choose. Fortunately, your kitchen remains unsuitable for neutron star sampling. These objects offer gravity, another temporary defeat. Neutron degeneracy and nuclear interactions can resist further compression, but only up to a point. What happens when even that support fails? In 1939, J. Robert Oppenheimer and George Volkoff study the properties of neutron stars using general relativity. Their calculations indicate that sufficiently massive neutron stars cannot remain stable indefinitely. That same year, Oppenheimer and Hartland Snyder analyze continuing gravitational collapse. Their model is highly idealized. They consider a spherical cloud of pressureless matter, simplifying the complicated physics of real stars. Yet the calculation reveals something extraordinary to a distant observer. the collapsing object's surface appears to slow as it approaches the critical radius. Its emitted light becomes increasingly red-shifted and faint from the viewpoint of falling matter. However, collapse continues. The star passes beyond a boundary from which signals can no longer escape to distant observers. The modern event horizon is taking shape. The phrase black hole still does not exist. Physicists speak instead about gravitational collapse, Schwarzschild singularities, or related mathematical structures. Many researchers remain skeptical about whether such extreme collapse occurs in nature. There are reasonable doubts. Real stars rotate. They contain pressure. They possess magnetic fields and complicated internal structures. Perhaps some neglected physical process always interrupts collapse before the strange relativistic boundary forms. That possibility cannot yet be dismissed. And then history interrupts physics. The Second World War begins in Europe in 1939. Research priorities shift dramatically, especially toward nuclear physics and military technologies. Oppenheimer himself will soon become associated with a very different chapter of 20th century science. Gravitational collapse moves away from the center of attention. For a while, the mathematical darkness waits again. Yet astronomy continues changing. Cosmic rays reveal energetic processes arriving from space. Radio technology develops rapidly. New detectors begin extending observation beyond visible wavelengths. Humanity is preparing instruments capable of discovering a violent universe that optical astronomy alone had largely concealed. This matters because black holes are dark only in a very particular sense. The horizon emits no ordinary escaping light from inside it. Matter outside can be spectacularly bright. Gas falling toward a compact object may collide, compress, and heat until it produces enormous amounts of radiation. A black hole can therefore advertise its presence through everything it does to its surroundings. The paradox is almost charming. To discover the darkest objects, astronomers will search for some of the brightest disturbances. Before that happens, another cosmic transformation must enter your story. During the 1920s, Edwin Hubble and others established that at least some spiral nebulae lie far beyond the Milky Way. The universe becomes populated by galaxies. Observations also reveal a systematic relationship between galactic distance and recession. Space itself participates in cosmic expansion. General relativity, originally developed to explain gravity, has become part of cosmology. Humanity now lives inside an evolving universe. Its galaxies contain billions of stars, and some stars must eventually exhaust the physical mechanisms supporting them against gravity. You stand outside beneath a wartime night sky. Perhaps distant engines hum beyond the horizon. Cold air carries the smell of smoke and damp ground, while familiar constellations remain overhead. Among those stars, gravity is conducting experiments no terrestrial laboratory can reproduce. Some stellar cores are collapsing. Some have already crossed horizons. Human mathematics has finally shown that such collapse may be possible. What humanity still lacks is convincing evidence that nature has actually done it. That evidence will arrive from an unexpected direction. Astronomers will stop relying only on visible light, and the universe will suddenly become much louder. After the Second World War, astronomy begins listening to a universe that human eyes had never been able to see. Radio technology has advanced rapidly during the war, and scientists now adapt antennas and receivers to peaceful questions about the sky. invisible wavelengths begin revealing celestial structures hidden from ordinary optical telescopes. You step into this new observational world beneath a broad metal dish. Wind moves across its framework with a low mechanical hum. Damp soil smells faintly beneath your shoes, while cables and electronic equipment replace much of the brass and polished glass of older observatories. The universe has acquired another voice. Radio astronomy itself had begun before the war. During the early 1930s, Karl investigated radio interference affecting transatlantic communications at Bell Telephone Laboratories. His unusual rotating antenna became famous for its appearance. It resembled a large skeletal structure mounted on wheels, earning the informal comparison to a merry-go-round. Jansky identifies radio emission arriving from the direction of the Milky Way. Our galaxy is broadcasting. Grote Reber later constructs a pioneering radio dish in his own backyard and surveys the radio sky. His work helps transform Jansky's discovery into a new branch of astronomy. This is a wonderfully appropriate beginning. One of humanity's great observational revolutions grows partly from a large homemade instrument standing beside someone's house. By the 1950s, radio sources are appearing across astronomical catalogs. Some correspond with recognizable objects. Others do not. Then certain compact radio sources produce an especially difficult puzzle. They look almost star-like through optical telescopes, yet their spectra and radio output seem peculiar. Astronomers eventually call them quasi-stellar radio sources, shortened to quasars. In 1963, Martin Schmidt studies the spectrum of the object 3C 223. Its spectral lines initially appear unfamiliar. Then Schmidt recognizes the pattern. They are ordinary hydrogen lines shifted dramatically toward longer wavelengths. The object possesses a large redshift. If that redshift reflects cosmic expansion, 3C273 must be enormously distant, yet it appears bright enough to be photographed with comparatively modest telescopes. The implication is staggering. This compact region must produce tremendous amounts of energy. You can imagine the quiet shock of realizing what the numbers demand. Paper lies across a desk. Spectral measurements sit under lamplight. Perhaps coffee has cooled somewhere nearby, while an apparently obscure pattern suddenly reorganizes itself. Distance transforms brightness into power. Quasars can outshine entire galaxies. Whatever fuels them must release energy with extraordinary efficiency from a relatively compact region. Nuclear fusion alone struggles to provide a convincing explanation for the observed behavior. Gravity returns. By this time, theoretical work on extreme relativistic objects has also revived. During the 1950s and 1960s, physicists including John Wheeler helped bring gravitational collapse back into serious discussion. Improved mathematical methods clarify the meaning of Schwarzschild's troublesome radius. The boundary is not simply a mathematical embarrassment. It represents something physical, an event horizon. Cross it inward, and every future directed path remains trapped within the black hole region. This does not mean gravity suddenly becomes an infinitely powerful suction force at the horizon for a sufficiently massive black hole. A freely falling observer might cross the horizon without encountering any locally dramatic marker. The terror belongs more to geometry than sensation. All roads forward lead deeper inward. In 1967, Wheeler famously helps popularize the term black hole. The phrase is wonderfully compact. A complicated relativistic object receives a name understandable without a page of tensor equations. The terminology spreads quickly. There is a quirky historical wrinkle here. Researchers still discuss earlier appearances and influences surrounding the phrase. So, assigning absolute invention to one dramatic moment can oversimplify its linguistic history. Still, Wheeler unquestionably helps make the name famous, and names matter. Once you can say black hole, the object becomes easier to discuss, teach, imagine, and search for. Meanwhile, quasars provide possible evidence for enormous black holes. Imagine gas falling toward a supermassive compact object at the center of a galaxy. The gas carries angular momentum, so it does not simply plunge straight inward. Instead, much of it forms a rotating accretion disk. Material spirals gradually toward the center. Frictional and magnetic processes convert gravitational energy into heat. The inner regions can reach extraordinary temperatures and produce radiation across the electromagnetic spectrum. The black hole remains dark. Its neighborhood blazes. This mechanism can be astonishingly efficient, converting a substantial fraction of infalling mass into radiation before material crosses the horizon. A feeding black hole can therefore become one of the brightest engines in the cosmos. The old dark star has transformed into something Michel could never have predicted. Then another observational revolution arrives from above Earth's atmosphere. X-rays are especially useful for studying extremely hot cosmic environments. Unfortunately for astronomers, Earth's atmosphere absorbs most astronomical X-rays. This is excellent for your health. It is inconvenient for telescopes. Detectors must be carried above much of the atmosphere using rockets, balloons, and eventually satellites. In 1962, a rocket experiment detects an unexpectedly bright celestial X-ray source in the constellation Scorpius. It becomes known as Scorpius X1. The X-ray sky is alive. Other sources soon appear. Some vary rapidly, indicating that their emitting regions must be compact. Large objects cannot coordinate dramatic brightness, changes faster than light can cross them. Time itself becomes a measuring tool. If something changes within milliseconds, the region responsible cannot span light years. Compact objects become increasingly important. Neutron stars receive spectacular confirmation in 1967 when Jocelyn Bell Burnell notices unusual repeating radio signals in data from a new radio telescope. The pulses are astonishingly regular. For a brief period, the possibility of artificial extraterrestrial signals is considered seriously enough that an early source receives the playful designation LGM, referring to little green men. Nature soon provides a less sociable explanation. Pulsars are rapidly rotating neutron stars whose beams sweep across Earth like cosmic lighthouses. The discovery proves that stellar remnants can reach extraordinary densities and remain observable. But neutron stars cannot explain every compact object. Some binary systems seem to contain unseen companions too massive to fit comfortably within neutron star limits. One system becomes particularly important. Cygnus X1 is a powerful X-ray source associated with a massive visible star orbiting an unseen companion. You return to Michel's old idea. Watch the visible star, measure its motion, calculate the mass of what pulls it. If the hidden companion is too massive to be a neutron star and emits no ordinary stellar light, a black hole becomes a compelling explanation. During the early 1970s, Cygnus X1 emerges as one of the strongest black hole candidates. Not everyone is immediately convinced. Uncertainties in stellar mass, distance, inclination, and models leave room for debate. Astronomers must build the case gradually. That caution is healthy. You're trying to prove the existence of something defined partly by its invisibility. By now, however, several independent stories are converging. General relativity permits black holes. Stellar evolution can produce gravitational collapse. Quasars require enormously powerful compact engines. X-ray binaries reveal unseen massive companions. The mathematical impossibility is becoming an astrophysical population. You stand beneath a radio telescope as evening deepens. Above you, the visible stars look almost unchanged. But the invisible sky has become violent. Radio waves cross the galaxy. X-rays stream from superheated matter. Pulsars flash with extraordinary precision. And somewhere inside those signals, black holes are finally beginning to reveal themselves, not by shining, by making everything around them impossible to ignore. Once black holes become serious astronomical candidates, a peculiar problem settles over the entire search. How do you prove that something invisible is truly there? You cannot place a black hole beneath a laboratory microscope. You cannot illuminate its surface because, according to general relativity, there is no ordinary solid surface to illuminate. Gravity provides the fingerprints. Cygnus X1 offers one of the earliest compelling investigations. The system lies thousands of light years away and contains a massive visible star known as HDE, TO268 ATX8. Yet the visible star moves. You watch its spectrum shift rhythmically as it travels toward and away from Earth. Those tiny changes allow astronomers to estimate the orbital motion and constrain the mass of the hidden companion. The method echoes John Michel's 18th century suggestion with almost eerie precision. An invisible object can betray itself through a visible partner. But there is more. The system produces powerful X-rays. Gas drawn from the massive star travels toward the compact companion. As material falls deeper into the gravitational field, it can become extremely hot and radiate strongly. You imagine the environment near the compact object. There is no gentle celestial silence here. Gas moves at tremendous speeds. Magnetic fields twist through plasma, while collisions and turbulence convert gravitational energy into radiation. You would hear nothing in the vacuum. Yet translated into human senses, the environment would seem ferocious. The accretion flow glows at temperatures reaching millions of degrees. From Earth, detectors record its X-rays. During the early 1970s, evidence increasingly favors a black hole interpretation for Cygnus X1. Estimates place the unseen object's mass above plausible neutron star limits. The case strengthens over subsequent decades as measurements improve. Astronomers still debate details, such as exact system parameters, because measuring masses in distant binaries requires assumptions about orbital inclination, stellar properties, and distance. Certainty arrives gradually. There is even a famous scientific wager attached to the system. Stephen Hawking and Kip Thorne made a playful bet concerning whether Cygnus X1 truly contained a black hole. Hawking deliberately bet against black holes, partly as insurance against his own research interests. If black holes did not exist, at least he could win something. By 1990, the evidence had become persuasive enough that Hawking conceded. The episode captures an important feature of science. Confidence is not the same as absolute proof. You gather independent measurements until alternative explanations become increasingly strained. Other candidate systems appear. The disk becomes a luminous laboratory. Its inner regions respond to gravity far stronger than anything naturally available near Earth. Astronomers examine spectra, brightness variations, orbital motion, and changes in X-ray emission. Every signal reveals something different. Fast variability can constrain the size of emitting regions. Spectral features can reveal temperatures and velocities. Orbital dynamics can estimate masses. Black holes become measurable without becoming directly visible. Then another possibility enters the investigation. Some black holes appear relatively quiet. If little matter is falling toward them, they may produce weak electromagnetic signals. Finding such objects requires watching what gravity does to nearby stars. This technique becomes especially powerful near the center of the Milky Way. Long before astronomers can track individual stars there precisely, radio observations identify an unusual compact source. In 1974, Bruce Ballack and Robert Brown discover a bright radio source associated with the galactic center. It becomes known as Sagittarius A. The asterisk is added because the source is considered particularly exciting, borrowing a notation sometimes used in atomic physics for excited states. Astronomers, it seems, are allowed occasional enthusiasm in punctuation. The center of the Milky Way is difficult to study using visible light. Dust fills the galactic plane and blocks much of the optical radiation traveling toward Earth. Infrared wavelengths provide a way through. As infrared detectors improve, astronomers begin resolving individual stars crowded around the galactic center. Now you can watch gravity directly. Teams led by researchers including Reinhard Genzel and Andrea Ghez spend years measuring stellar positions with extraordinary precision. The work demands patience. Earth's atmosphere blurs incoming light. Stars crowd together. Instruments must repeatedly measure tiny changes across many observing seasons. You stand inside a modern observatory dome. Cooling equipment hums softly. Metal railings feel cold beneath your hand, while electronics replace the smell of photographic chemicals familiar to earlier generations. Outside, mountain air is thin and dry. The telescope turns toward Sagittarius. Night after night becomes year after year. Then the stellar paths begin forming unmistakable curves. One star, commonly called S2, proves especially valuable. It completes an orbit around the central object in roughly 16 years. Near its closest approach, it moves at several thousand kilometers per second. Something enormously massive occupies the center. Yet that mass produces almost no ordinary visible light of its own. Orbital measurements indicate roughly 4 million solar masses concentrated within an extremely small region. Alternative explanations become increasingly implausible. A dense cluster of ordinary dark objects would struggle to remain stable under such conditions. A supermassive black hole provides the natural explanation. In 2020, Genzel and Ghez share part of the Nobel Prize in Physics for work connected with the discovery of a supermassive compact object at the galactic center. The invisible has become something you can weigh. Elsewhere, astronomers discover evidence for black holes in many galaxies. Gas and stars orbit rapidly around compact central regions. Active galactic nuclei produce enormous luminosities. Jets emerge from environments surrounding some central objects and stretch thousands of light years. The jets create another common misconception. If nothing escapes from inside a black hole, how can a black hole produce a jet? The material in these jets does not emerge from behind the event horizon. Instead, complicated processes involving accretion disks, magnetic fields, and rotating black holes can redirect some surrounding matter outward before it crosses the horizon. Black holes are not cosmic vacuum cleaners either. from sufficiently far away. Their gravity behaves like the gravity of any object with the same mass. If the Sun could somehow become a black hole without changing its mass, Earth's orbit would remain approximately unchanged. You would have other problems. The sudden absence of sunlight would rank fairly high among them. This distinction matters because popular images often portray black holes as objects roaming through space and swallowing everything nearby. Reality is quieter. Most objects never approach closely enough to be captured. A black hole can orbit peacefully with a companion for millions or billions of years. By the late 20th century, astronomers possess a growing population of stellar mass and supermassive candidates. Yet one dream remains almost absurdly ambitious. Could humanity ever detect the event horizon itself? The horizon of Sagittarius A appears unimaginably small from Earth. Even enormous optical telescopes cannot resolve it, but astronomy has learned a recurring lesson. When one telescope is too small, connect many. When visible light cannot answer, use another wavelength. And when an object refuses to show its surface, observe the shadow that gravity carves into surrounding light. Soon, humanity will attempt exactly that. Before the image arrives, however, black holes will reveal an even stranger side. Quantum physics will ask whether they are truly black forever. The black hole has now traveled an extraordinary distance through human thought. It began as an 18th century speculation about dark stars, disappeared from serious attention, returned through relativity, and finally emerged as an observable inhabitant of the universe. But the largest surprise is still waiting. Black holes are not merely the remains of dead stars. Some appear to shape the lives of entire galaxies. You begin close to home, at the center of the Milky Way. Sagittarius A contains roughly 4 million times the mass of the Sun. That sounds enormous until you compare it with the black holes occupying other galactic centers. Some contain hundreds of millions of solar masses. Others reach billions. The question becomes unavoidable. How did they become so large? You travel backward through astronomical history to the strange quasars discovered during the 20th century. Their tremendous luminosities now make more sense if matter is falling toward supermassive black holes. Yet that explanation creates another puzzle. Some quasars exist at enormous cosmic distances because light takes time to travel. Observing distant quasars means seeing them when the universe was much younger. Massive black holes therefore formed surprisingly early. You can picture one of those young galaxies. There are no quiet spiral arms resembling the modern Milky Way. Gas flows chaotically through a dense environment. Stars form rapidly, while gravitational interactions disturb the developing system. At the center, matter approaches a growing black hole. Gas does not simply fall vertically into darkness. It usually carries angular momentum. The material therefore spreads into a rotating accretion structure, where internal stresses gradually move angular momentum outward and allow some gas to spiral inward. The deeper it falls, the more gravitational energy becomes available. The disk becomes hot, very hot. Radiation pours outward across wavelengths ranging from infrared through visible and ultraviolet light, sometimes reaching X-rays. If you could somehow hear this region through an imaginary translation of electromagnetic activity into sound, tranquility would not be the first word that came to mind. Yet from millions of light years away, everything appears silent. You only receive photons around some actively feeding supermassive black holes. Powerful jets extend far beyond the central galaxy. Magnetic fields play an essential role in launching and shaping these flows. The precise details remain an active field of research. Astrophysicists continue studying how magnetic fields, accretion states, and black hole spin combine to produce the observed variety of jets. Here uncertainty is not a weakness. It is where the frontier lives. The black hole itself may also rotate. Roy Kerr discovered an exact solution to Einstein's equations for a rotating black hole in 1963. This turns out to be extremely important because real astrophysical objects almost always possess angular momentum. A rotating black hole differs from the simpler Schwarzschild case. Outside its horizon lies a region called the ergosphere, where space-time is dragged around by rotation. You cannot remain stationary there relative to distant observers. Space-time itself insists upon movement. This effect is called frame dragging. It sounds like something invented for science fiction, yet it follows naturally from general relativity. In principle, rotational energy can be extracted from a spinning black hole through processes occurring outside the horizon. Roger Penrose described one theoretical mechanism in 1969. Later work connects black hole rotation with electromagnetic mechanisms that may help power astrophysical jets. The darkness has become an energy reservoir. Meanwhile, astronomers begin discovering a striking relationship between supermassive black holes and the galaxies surrounding them. The mass of a central black hole correlates with properties of the galaxy's central stellar bulge, including the characteristic velocities of its stars. This suggests some form of shared evolution. The black hole and galaxy somehow grow together. But which controls which? The answer is complicated. Galaxies supply gas that feeds black holes. Growing black holes can release enormous amounts of energy into surrounding gas through radiation, winds, and jets. That energy can heat material and influence future star formation. Astronomers call these processes feedback. Imagine a galaxy attempting to build new stars from cold gas. An active central black hole releases energy into its surroundings. Some gas heats or escapes. Star formation may slow. In other circumstances, compression associated with energetic activity might encourage localized star formation. Nature rarely offers a single simple switch. Researchers still debate how dominant different feedback mechanisms are across various galaxy types, masses, and cosmic periods. The broad connection, however, has become difficult to ignore. A region smaller than the solar system can influence structures spanning tens of thousands of light years. Scale becomes almost absurd. There is a quirky historical reversal hidden here. For much of astronomy, galaxies were considered collections of stars, while black holes seemed like exotic additions. Now, central black holes appear to be important participants in galactic evolution. The tiny darkness may help regulate the enormous city around it. You can see especially dramatic examples on giant elliptical galaxies. At the center of the galaxy, M87 lies a black hole containing billions of solar masses. A powerful relativistic jet extends from its central region. The galaxy itself sits within the Virgo cluster, surrounded by hot gas visible in X-rays. Energy from the central engine interacts with that environment. Black holes are no longer isolated endpoints of stellar death. They belong to cosmic ecosystems. The mystery deepens when you look toward the early universe. Astronomers have identified luminous quasars existing when the cosmos was less than 1 billion years old. Some already contain black holes with masses approaching or exceeding 1 billion suns. How can something grow that quickly? One possibility begins with the remnants of the earliest generations of massive stars. These stellar seeds could accrete matter and merge repeatedly. Another possibility involves direct collapse, where enormous clouds of primordial gas form much heavier black hole seeds without passing through ordinary stellar evolution first. Other scenarios combine several pathways. Observations are beginning to test these possibilities, but the full origin story remains unsettled. The James Webb Space Telescope has extended observations of early galaxies and active galactic nuclei deeper into cosmic history, sharpening questions about how rapidly black holes and galaxies assembled. Once again, a new instrument changes the question. You have seen this pattern before. The astrolabe refined naked-eye astronomy. The telescope revealed moons and mountains. Spectroscopy exposed stellar chemistry. Radio antennas uncovered quasars. X-ray detectors found compact binaries. Infrared instruments tracked stars around Sagittarius A. Each technological extension reveals a universe that was already there, waiting beyond the limits of human senses. Now you stand beneath a modern observatory sky. The Milky Way arches overhead, pale and textured in the darkness. Cool air touches your face, and distant equipment produces a low electrical hum. Near the center of that glowing band sits Sagittarius A. You cannot see the black hole with your eyes, yet stars orbit it. Gas heats around it. Space-time bends around it. Across the wider universe, billions of galaxies may contain similar central objects. The mathematical curiosity has become part of cosmic architecture. But an even stranger question remains. General relativity describes what happens to matter falling toward a black hole. Quantum physics describes matter and radiation on microscopic scales. When you force those two theories toward the same horizon, they begin telling a story nobody expected. A perfectly black object may not remain perfectly black, and darkness itself may slowly evaporate. Once black holes become accepted as physical objects, they create a problem deeper than proving that they exist. Two extraordinarily successful descriptions of nature meet near the horizon, and they do not fit comfortably together. One is general relativity. It describes gravity, space-time, planets, stars, galaxies, and the large-scale structure of the universe with remarkable accuracy. The other is quantum theory. It describes atoms, particles, radiation, and microscopic interactions with equally remarkable success. A black hole demands both. You approach the horizon only in imagination. For a sufficiently massive black hole, the region can appear surprisingly uneventful to someone falling freely. There need not be a glowing wall or solid boundary. You simply continue falling. Yet something profound has happened. Once you cross the event horizon, returning to the external universe is no longer among your possible futures according to classical relativity. The horizon is a causal boundary. This raises an uncomfortable question. What happens to information carried by everything that falls inside? Before that puzzle fully emerges, another connection appears through thermodynamics. During the early 1970s, Jacob Bekenstein begins thinking seriously about black holes and entropy. Entropy can be understood in several related ways, including as a measure connected with the number of microscopic configurations compatible with a macroscopic state. Black holes seem troublesome because they can swallow matter carrying entropy. Imagine dropping a warm object into one. The object's energy crosses the horizon. Its entropy appears to disappear from the observable universe. Could the total entropy outside decrease? That would threaten the second law of thermodynamics. Bekenstein proposes something bold. Perhaps a black hole itself possesses entropy. Even stranger, that entropy should be related to the area of its event horizon rather than the volume hidden inside. Area becomes information. The idea initially seems suspicious. A black hole with entropy should also possess a temperature, and an object with temperature should radiate. But black holes are supposed to absorb everything and emit nothing. There is your contradiction. Stephen Hawking initially doubts Bekenstein's interpretation. Then he performs a quantum calculation around a black hole. In 1974, the calculation gives him an answer he had not expected. Black holes radiate. You can imagine the quiet atmosphere surrounding such theoretical work. Pages turn beneath your fingers. Chalk moves across a board, producing that dry, scratching sound familiar in physics departments. Outside, ordinary weather continues. Inside the equations, eternal darkness has begun glowing. The phenomenon becomes known as Hawking radiation. A common popular explanation describes particle pairs appearing near the horizon, with one falling inward while the other escapes. That picture can provide intuition, but it should not be mistaken for the complete derivation. The actual phenomenon arises from quantum fields in curved space-time and from how different observers define particle states. The mathematics is subtler. The conclusion is beautifully simple. A black hole has a temperature. For astrophysical black holes, that temperature is extraordinarily low. A black hole with roughly the Sun's mass would possess a Hawking temperature of only about 60 billionths of a Kelvin. Larger black holes are colder still. The supermassive black holes inhabiting galactic centers are therefore extremely poor heaters. You would not choose one for a winter bedroom, because the current universe contains background radiation warmer than most astrophysical black holes. They presently absorb more energy than they lose through Hawking radiation, but the universe is expanding over immense future timescales. Cosmic backgrounds cool. Eventually, isolated black holes could lose more energy than they gain. They begin evaporating. As a black hole loses mass, its temperature rises. The process accelerates. For stellar and supermassive black holes, evaporation times are almost incomprehensibly long, vastly exceeding the present age of the universe. A solar mass black hole would require roughly 10⁻⁷ years to evaporate through the simplest semi-classical estimate. Supermassive examples endure enormously longer. The future has patience. Yet Hawking's discovery creates a much deeper problem. Suppose you throw a book into a black hole. You do not need to choose an especially good book. Its detailed physical state contains information. In ordinary quantum mechanics, information describing a closed system is not simply erased from reality. But Hawking's original calculation suggests the outgoing radiation is thermal and does not obviously preserve detailed information about what formed or entered the black hole. Eventually, the black hole evaporates. Where did the information go? This becomes the black hole information paradox. It sounds abstract. It is actually a collision between foundational principles. General relativity suggests information can disappear behind a horizon and perhaps terminate at a singularity. Quantum mechanics strongly resists fundamental information destruction. Both theories work exceptionally well where tested. Something must give. For decades, physicists argue over possibilities. Perhaps information truly disappears, requiring quantum mechanics to be modified. Perhaps information somehow emerges within Hawking radiation. Perhaps a remnant survives after evaporation and stores what fell inward. Perhaps the classical picture of the black hole interior is incomplete. The debate becomes one of theoretical physics' most persistent problems. In the 1990s, ideas involving holography begin reshaping the conversation. Gerard 't Hooft and Leonard Susskind develop arguments suggesting that information describing a region might be represented on a lower dimensional boundary. Black hole entropy had already offered a tantalizing clue because it scales with horizon area. Then string theory provides another major development. In 1996, Andrew Strominger and Qumrun Vafa calculate the entropy of certain idealized black holes by counting underlying quantum states within string theory. Their result reproduces the expected Bekenstein-Hawking entropy. This does not solve every astrophysical black hole problem, but it suggests that the mysterious entropy really can correspond to microscopic quantum states. The horizon may encode more than classical relativity reveals. Later, gauge gravity dualities strengthen the idea that gravitational systems can have equivalent descriptions without gravity in fewer dimensions. These theoretical developments encourage many physicists to believe information is ultimately preserved. Exactly how information escapes from realistic evaporating black holes remains an active and technically difficult question. Recent theoretical work involving quantum extremal surfaces and related calculations has reproduced an expected pattern called the page curve in certain models. This suggests that information may indeed be encoded in Hawking radiation. Yet scholars continue debating what these calculations imply about actual black hole interiors and the full quantum theory of gravity. The horizon remains intellectually restless. There is another complication. Classical general relativity predicts singularities under broad conditions, as work by Roger Penrose, Stephen Hawking, and others helped establish. At a singularity, familiar classical descriptions break down. You should be cautious here. A singularity is not necessarily a literal infinitely dense point that established physics fully understands. It signals that the classical theory has reached the edge of its applicability. Something more complete is needed: quantum gravity. Candidate approaches include string theory, loop quantum gravity, and other frameworks. None has yet achieved universally accepted experimental confirmation as the final description. Black holes therefore become laboratories you cannot enter, but desperately want to understand. They connect thermodynamics, quantum mechanics, information theory, gravity, and cosmology. An object once dismissed as mathematical pathology now points toward physics beyond current theories. You return to the quiet night. The air feels cool against your hands. Somewhere nearby, computers hum while telescopes collect photons that have traveled across immense distances. Above you, black holes remain visually dark, yet theoretically they have become almost unbearably bright with questions. Do horizons store information? What replaces the singularity? How does spacetime emerge at quantum scales? Does Hawking radiation preserve everything that falls inward? No telescope alone can answer all of this. But black holes are about to offer another kind of evidence. Instead of watching matter orbit them, humanity will detect spacetime itself, trembling as two black holes collide. And soon after that, an Earth-sized virtual telescope will attempt something generations once considered impossible. It will look directly toward the edge of darkness. For most of their history, black holes reveal themselves through what they do to something else. A companion star moves around an invisible mass. Gas heats while falling inward. Galactic centers release enormous radiation as matter approaches unseen horizons. Then humanity learns to detect gravity itself. The possibility begins with Einstein. General relativity predicts that accelerating masses can produce ripples in space-time called gravitational waves. These disturbances travel outward at the speed of light. Einstein predicts them in 1916. For decades, however, detecting them seems almost absurdly difficult. Gravity is extraordinarily weak compared with other fundamental interactions. By the time gravitational waves from distant astronomical systems reach Earth, their effects are tiny. You need an instrument capable of measuring changes smaller than an atomic nucleus across kilometer-scale distances. That sentence sounds unreasonable. Scientists build the instrument anyway. The Laser Interferometer Gravitational Wave Observatory, better known as LIGO, operates two major detectors in the United States, one in Louisiana and another in Washington State. Each facility contains two long arms arranged at right angles. Laser light travels through vacuum tubes, reflects from suspended mirrors, and returns to interfere with itself. You enter one of these facilities in imagination. The corridors feel clean and controlled. Machinery produces a low background hum, while polished equipment sits isolated from ordinary vibration. Outside, wind moves across the landscape. Inside, engineers are trying to measure space-time stretching. Passing gravitational waves alter the relative lengths of the interferometer arms by unimaginably small amounts. The challenge is not merely sensitivity. Earth itself is noisy. Seismic motion shakes the ground. Trucks travel along distant roads. Ocean waves create subtle vibrations. Thermal motion disturbs equipment. Even molecules remaining inside imperfect vacuum systems can matter. The universe whispers beneath an orchestra of local inconvenience. Initial versions of LIGO do not detect gravitational waves. That is not failure. Engineers learn how to control noise, improve mirrors, strengthen lasers, and refine isolation systems. Advanced LIGO begins observations in 2015. Then, on September 14th, something passes through Earth. At 09:50:45 Coordinated Universal Time, both LIGO detectors record a short signal. Its frequency rises rapidly. Its amplitude increases. Then it ends, translated into sound. The pattern produces a brief rising chirp. You can almost hear it. Two black holes have been spiraling around each other as they lose orbital energy through gravitational radiation. Their separation shrinks. They move faster, orbit more rapidly, and produce stronger waves. Then they merge. The final black hole settles into a stable state. The event receives the name GW15-14. Analysis indicates that the original black holes contained roughly 36 and 29 solar masses, according to the early reported estimates. The final black hole contains about 62 solar masses. Several solar masses have effectively become gravitational wave energy. For a fraction of a second, the power carried by those waves is extraordinary. The merger occurred more than 1 billion light-years away. Its gravitational signal traveled across expanding space before gently changing the lengths of instruments on Earth by less than a proton's width. Humanity has heard two black holes collide. The detection is announced publicly in February 2016. It provides the first direct detection of gravitational waves and the first observation of a binary black hole merger. The result also reveals something astrophysicists had not established clearly beforehand. Stellar mass black holes around 30 solar masses can form and participate in merging binary systems. A new observational field opens immediately. Other detections follow. Black hole mergers arrive with different masses and properties. Neutron-star collisions join the catalog. Gravitational wave astronomy allows you to study objects that may produce little or no ordinary light. Darkness has acquired sound, at least after mathematical translation into audible frequencies. There is a charming detail hidden in this enormous achievement. The signal lasted only a fraction of a second in its most prominent portion. Decades of engineering helped humanity listen for one tiny chirp. Astronomy often rewards unreasonable patience, but another project is attempting something equally audacious. Instead of hearing black holes, astronomers want to see the region immediately surrounding a horizon. The problem is resolution. Even supermassive black holes appear extremely small from Earth. Sagittarius A is enormous physically, but it lies roughly 26,000 light-years away. M87's central black hole is vastly more massive, yet the galaxy lies tens of millions of light-years away. No single conventional telescope can resolve the required scale, so astronomers effectively construct a telescope the size of Earth. The Event Horizon Telescope is not one physical dish. It is a network of radio observatories distributed across the planet. The technique is called Very Long Baseline Interferometry. Separate telescopes observe the same source, while exquisitely precise atomic clocks record timing information. Their data can later be combined computationally. The effective resolution depends on the enormous distances between observatories. You now stand at several locations at once in imagination. Cold wind sweeps across a high mountain. Dry air presses against your lips in a desert. At another site, snow surrounds instruments working beneath an exceptionally clear atmosphere. Every telescope must cooperate. Weather matters, timing matters, data storage matters. Even transporting recordings becomes part of the experiment. During observing campaigns, the network collects enormous quantities of information. Some data from the South Pole cannot simply be transmitted quickly through ordinary internet connections. Physical storage devices must eventually travel. The image of a black hole partly depends upon shipping boxes full of hard drives. Cosmic grandeur occasionally requires logistics. In April 2019, the collaboration releases the first horizon-scale image of a black hole environment. The target is M87 Cleide. You see a bright, asymmetric ring surrounding a dark central region. It is tempting to call the darkness the event horizon itself, but the description requires care. The central feature is commonly called the black hole shadow. Strong gravitational lensing bends light around the black hole, while photons near unstable trajectories contribute to the observed ring structure. The shadow is larger than the horizon. Still, the image probes precisely the extreme gravitational environment predicted by relativity. A century after Schwarzschild wrote his solution, humanity sees its consequences on horizon scales. Then, in 2022, the Event Horizon Telescope collaboration releases an image of Sagittarius A. This target presents different challenges. Its black hole is much less massive than M87 Cleide, so material near it changes more quickly during observations. Imagine photographing a restless subject using a camera assembled from telescopes across Earth. The reconstruction becomes extremely difficult. Multiple imaging methods are used to ensure that persistent structures are not merely artifacts of one algorithm. Again, the instrument itself must be interrogated. Galileo faced a related problem when skeptics wondered whether his telescope produced misleading celestial appearances. The technology has changed. The philosophical caution has not. Do you trust what your instrument shows? Only after calibration. independent methods, repeated testing, and comparison with physical predictions. The resulting observations agree impressively with general relativity. Yet uncertainty remains in important areas. Researchers continue investigating accretion physics, magnetic fields, black hole spin, jet formation, and whether subtle deviations from relativity might eventually become measurable. Future gravitational wave observatories will extend sensitivity. Space-based interferometers are expected to study much larger black hole systems at lower gravitational wave frequencies. Improved horizon-scale arrays may produce sharper images and perhaps moving sequences of matter near black holes. You stand outside once more. The night air is cold, and the Milky Way stretches overhead as it did for the first human sky watchers. But your relationship with that sky has changed beyond recognition. Ancient observers watched points of light. Babylonians recorded their patterns. Greek thinkers shaped them with geometry. Medieval astronomers refined measurements. Copernicus moved Earth. Galileo extended vision. Newton unified gravity. Einstein curved space-time. Modern instruments finally detected its vibrations. And now you have seen the shadow cast by an object that earlier generations considered physically impossible. One final journey remains. You must carry these dark objects backward toward the beginning of cosmic history, then forward into a future where stars fade and galaxies grow quiet. Black holes may have accompanied the universe almost from its infancy. They may also become some of its final enduring inhabitants. You have followed black holes from an idea that seemed almost unreasonable to objects now measured across the universe. Yet their story may begin much earlier than stars. To explore that possibility, you must travel backward through cosmic history, beyond galaxies, beyond the first stellar light, toward a universe that is hot, dense, and extraordinarily young. Modern cosmology traces cosmic expansion backward toward an early state unlike anything familiar today. In 1929, Edwin Hubble published observations establishing a relationship between galactic distances and recession velocities, building upon earlier theoretical and observational work. The universe was expanding. If you reverse that expansion mathematically, matter and radiation become increasingly concentrated. Later evidence makes this evolving universe difficult to escape. In 1965, Arno Penzias and Robert Wilson report mysterious microwave noise appearing stubbornly in their radio antenna. They check the equipment. They investigate possible interference. Even pigeon droppings inside the antenna become part of the troubleshooting story. Cosmology occasionally depends upon cleaning. The persistent signal is eventually recognized as the cosmic microwave background, relic radiation from the early universe. Today, you observe that radiation after more than 13 billion years of cosmic expansion. It provides a remarkably detailed picture of the universe when atoms were forming and light began traveling freely across large distances. But black holes may reach farther backward still. One possibility involves primordial black holes. Unlike ordinary stellar black holes, these hypothetical objects would not require dying stars. They could form from sufficiently large density variations or other processes in the extremely early universe. Their possible masses depend upon the formation mechanism. Some theoretical scenarios allow very small primordial black holes. Others permit objects with stellar or much greater masses. None has yet been conclusively identified as primordial. That uncertainty matters. Primordial black holes have been proposed as possible contributors to dark matter, the unseen matter inferred through gravitational effects throughout galaxies and cosmic structure. Observations strongly constrain how abundant primordial black holes can be across many mass ranges. Gravitational lensing surveys, cosmic background measurements, dynamical arguments, and other observations narrow the possibilities. Still, some parameter ranges remain scientifically interesting. The question remains open. Did the early universe manufacture black holes before stars existed? If so, some ancient survivors might still move silently through galaxies today. There is another early mystery. Supermassive black holes appear surprisingly soon in cosmic history. You have already encountered distant quasars powered by enormous central objects. Their light shows that some black holes accumulated tremendous masses within the universe's first billion years. Modern observatories are pushing these measurements earlier. The James Webb Space Telescope observes distant galaxies at infrared wavelengths, allowing astronomers to investigate young cosmic systems whose light has been stretched during expansion. Some observations reveal active galactic nuclei surprisingly early. Exactly how quickly the first massive black hole seeds formed remains uncertain. Perhaps the first generations of massive stars produced them. Perhaps enormous gas clouds collapsed directly. Perhaps dense stellar environments created seeds through repeated collisions and mergers. Several pathways may operate. The universe rarely promises a single origin story. Whatever their beginnings, black holes become woven into cosmic evolution. Stars create stellar mass black holes. Galaxies merge and bring central black holes together. Those black holes can eventually merge too, sending gravitational waves across space-time. Gas feeds them. Their energetic surroundings influence galaxies, and then the universe continues expanding. Here your journey turns toward the future. Observations indicate that cosmic expansion is accelerating. A discovery established during the late 1990s through studies of distant Type Ia supernovae and supported by other cosmological evidence. The cause is described broadly as dark energy. That name is partly a confession. Scientists can measure important properties of cosmic acceleration without yet knowing the underlying nature of whatever produces it. If the simplest current cosmological picture remains approximately correct, distant gravitationally unbound galaxies will eventually recede beyond our observable reach. The local cosmic neighborhood will become increasingly isolated. Star formation will decline as usable gas becomes scarce. Existing stars will age. The night sky of the unimaginably distant future will grow darker. You can imagine standing on a hypothetical surviving world. Although ordinary planets may not remain habitable for anything approaching these timescales, the sky would no longer resemble yours. Many galaxies would have disappeared beyond the observable horizon. Stellar populations would become dominated by long-lived remnants. White dwarfs, neutron stars, and black holes would outlast the bright stellar era. Eventually, even stars fade from cosmic prominence. Black holes remain. Stellar mass black holes can survive for timescales vastly exceeding the current age of the universe. Supermassive black holes endure far longer. If Hawking's semi-classical calculation describes their ultimate fate, however, even they are temporary. A black hole slowly radiates for an enormous span of time. The process is almost negligible. Then mass gradually declines, temperature rises, evaporation accelerates. The largest black holes may require around 10^100 years, or even longer depending on mass, before disappearing through Hawking radiation. Numbers like this resist imagination. The present universe is only about 1.381 times 10 years old. Compared with black hole evaporation times, cosmic history has barely begun. There are uncertainties here, too. Predictions about the extremely remote future depend upon assumptions concerning proton stability, dark energy, particle physics, quantum gravity, and whether currently known laws remain applicable across such astonishing durations. No observation can directly test a trillion generations of cosmic evolution. You are extrapolating, carefully but inevitably. Perhaps quantum gravity changes the final stages of evaporation. Perhaps stable remnants survive. Perhaps information emerges completely within Hawking radiation. Perhaps the interior structure of black holes differs radically from the classical picture. Physicists still disagree. That disagreement returns you to the most important lesson in this entire journey. Scientific knowledge grows through uncertainty rather than by avoiding it. Think of how far you have traveled. The earliest sky watchers could observe planets, eclipses, seasons, and stars. They possessed no reason to imagine an event horizon. Greek astronomers introduced geometry into cosmic models. Medieval scholars preserved, tested, and expanded mathematical astronomy. Copernicus moved Earth away from the center. Tycho improved measurement. Kepler abandoned perfect circles. Galileo pointed glass toward the heavens. Newton connected falling objects with planets and stars. Michel imagined invisible suns. Herschel expanded the stellar universe. Spectroscopy transformed light into physical evidence. Einstein made space-time dynamic. Schwarzschild found an unexpected doorway inside the equations. Chandrasekhar discovered that stellar support has limits. Oppenheimer and Snyder followed collapse beyond familiar matter. Radio astronomy uncovered quasars. X-ray astronomy exposed compact gravitational engines. Stellar orbits revealed invisible masses. Gravitational waves allowed you to hear black holes merge. The Event Horizon Telescope finally showed you their shadows. Each generation extended human senses, and each extension made the universe stranger. There is gentle irony in that progression. Human beings once placed themselves near the center of an orderly cosmos. Now you understand yourself as a small biological species living on one planet around one ordinary star, inside one galaxy among hundreds of billions. Near your galaxy's center waits a black hole containing millions of solar masses. It does not know you are here, yet you have measured it. That may be the most remarkable part. You cannot touch a black hole. You cannot send a message from behind its horizon and receive an answer. You cannot reproduce one safely inside a terrestrial laboratory. Still, mathematics, observation, and patient comparison allow you to know something real about objects separated from you by thousands or billions of light years. The universe has been discovered twice. First, matter formed stars, galaxies, planets, and black holes through billions of years of cosmic evolution. Then, much later, one small species began looking upward and slowly learned what had already happened. And the discovery is unfinished. Future gravitational wave detectors may hear mergers that current instruments cannot detect. Sharper horizon-scale observations may reveal moving structures around black holes. New surveys may uncover isolated black holes drifting through the Milky Way. Early universe observations may clarify how the first massive seeds formed. Quantum gravity may eventually explain what classical singularities are trying to tell you. perhaps the greatest surprise has not arrived yet. For now, you return to the oldest instrument humanity ever possessed. Your eyes. You step outside beneath a dark sky. Cool air settles against your face, while the ground feels firm and quiet beneath your feet. Somewhere nearby, leaves move softly in the night breeze. The stars shine above you. Between them lies darkness. Once darkness meant only absence. Now you know better. Some darkness has mass. Some darkness bends light. Some darkness can collide strongly enough to shake space-time across 1 billion light-years. And somewhere beyond your sight, black holes continue their patient journeys through a universe still becoming known. The sky grows quieter now. You do not need to solve its remaining mysteries tonight. The galaxies can continue drifting while the stars follow their ancient paths. Let the great distances soften. Let the equations fade. The telescope dome closes. The instruments become still, and the last quiet lights disappear from the observatory. Far beyond Earth, space-time continues curving around silent horizons. Nothing asks you to follow. You can simply remain beneath the stars, breathing slowly as the universe carries on without hurry. The darkness is no longer empty, and for tonight, it can simply be peaceful.